Hello, this video is about superimposing and foliating inertial spacetime diagrams. And to cut to the chase, by the end of this video I'm going to be comparing this spacetime diagram where we foliate by the plane of simultaneity to this spacetime diagram where we foliate by the past light cone. So let's get into that by starting with this space-time diagram. And if you have not been studying special relativity for long, then you probably won't recognize this diagram. But if you have been, you should recognize that this is what is a typical explanation for what happens from the in the twin paradox. This observer, or there's a stay-at-home twin that that travels from event O. O is origin and D is destination over here, while the traveling twin goes from event O to event T, the turnaround event, and then he turns around and comes back and meets back with the stay-at-home twin at the destination. Now, what happens in these explanations is they generally try to show the isoclines of simultaneity for the turnaround twin. And the isoclines of simultaneity are, it's a different process than a standard rotation. A standard rotation looks like this. But a hyperbolic rotation looks, well, I can't really show it. I can't really stretch out the paper in this way. But basically, you pull on this part and you crunch on this part, which causes these points to go in, these points to go in, these points to go out, and these points to go out. But all the other points follow hyperbolas, which is why it's called a hyperbolic rotation. It's more of a skew operation than a rotation, but it does have the effect of, if you just look, say, at this line here, it moves this way and then this way. So for a little while, it looks just like a rotation because it's going from there to there. So what happens during this hyperbolic rotation from this hyperbolic rotation of the space-time is that when the twin accelerates at the beginning, his lines of simultaneity go from here to here. And then when he turns around on the way back, his lines of simultaneity rotate from there to there. So what happens is they describe this, a lot of times what people will describe is just this period of time, the A, B, and C, just being skipped by the twin that is experiencing the turnaround. Those events just are skipped. Now some will actually go to not that graph, this graph. They will go and I will say, well, from his point of view, we will get this period from O to the turnaround event. He will be stationary from his own perspective, so he would go from O to turnaround, and the amount of time he actually experiences, T divided by gamma, and gamma is a quantity of actually, most of the time you see it expressed in terms of the V over C, which is, so it's 1 over the square root of 1 minus V over C squared. You can also express it in terms of a quantity called the rapidity, and it is the hyperbolic cosine of the rapidity. Much as if you have a line of slope m, the trigonometric, or the circular cosine of the angle is equal to 1 over square root of 1 plus m squared. So this is the hyperbolic version, and that is the circular version of the trigonometry. But anyway, so if this is t prime equals t over gamma, then the distance between this event here and, okay, so we skipped straight from event A to event C, right? So the distance here is velocity times t prime, which is the distance over gamma. It's a shorter distance, and so this graph, oh, and I should mention also this little difference. Cosine theta is always less than or equal to 1, but cosh phi is always greater than or equal to 1. So there's a little difference there. So when I say d over gamma, this is a shorter distance than, so we've shortened the distance from t to a. So some people been talking to a guy that says, well, this graph is not acceptable, and I agree. We need to have some kind of representation of A, B, C. And so in order to do that, what about this graph? And we will actually have the B point is right in the middle when the guy has achieved, when he is at the same velocity as the Earth, then this will reach its full uncontracted distance, d equals vt, and but we'll still have d equals vt prime for both events A and C. And so there'll be this sudden popping out and then popping in again at that time during the turnaround event. Yes, this is one way of doing it, but I want to show the full scope of things. And in order to do that, I'm going to show 3 different space-time diagrams. The first one, the outbound observer goes from event O, the origin, to T, the turnaround event. And we have these events A, B, and C. During that, at the beginning of that turnaround event, you can see A, that event there, is simultaneous with the turnaround event. And then during the turnaround event, we're going to go to this graph here. Now we can see that we have the origin, the turnaround, and the destination event. And at this moment in time, B is simultaneous with the turnaround event. And then we're going to show one more space-time diagram. This one here, and I guess now during this part of the trip, the TD portion of the graph is vertical, meaning that the stay-at-home or the traveling twin is stationary, but the Earth is approaching. And this turnaround, at this point, the turnaround event is simultaneous with point C, or simultaneous with event C, if you please. Okay, now I'm trying to hold these graphs up to the light, and so maybe you can see this, that when it was point A, it was a little bit closer to the turnaround event. Point B was a little further from the point turnaround event, and then point C comes back closer to the turnaround event again. But at the same time, where these lines intersect the past light cone, we have events F1, F2, and F3. Now F1, F2, and F3 are what are the events that are actually observed from the turnaround event. So from their perspective, the Earth travels along this line out to F1, and then during the turnaround event, the Earth will recede both in space and time to point F3, and then during this part of the journey, he will see Earth come along this direction here. until he reaches Earth at this point here. So my proposal for the space-time diagram is this is what I meant at the beginning when I said superimposing and foliating inertial space-time diagrams. By superimposing this graph for the outbound journey, this graph for the turnaround as he becomes co-stationary with the Earth twin, and this graph which describes the return journey. By superimposing those, we can get either this graph by foliating along the simultaneity plane, or we can get this graph by foliating along the past light cone. Now, in my opinion, this graph is better because this represents what the traveling twin will actually experience, viscerally experience. This one, when he is turning around, he will actually see the image of Earth lurch away from him, from this point to this point. He will definitely not see this sudden go away, come back behavior. Also, that go away, come back behavior of B going, or of going from C to just a little ways out to B and then back to A again, is much smaller, much less, much more subtle than what happens here as it goes from, as we go from F1, F2, F3. I was making this graph earlier when I was planning the video, but I think it's useful now to show the magnitude of the effects of the difference between moving from here to here versus moving from here to here. This is a much, much more subtle effect than moving across there. Now, you may be wondering, if this is such a big effect, why do we never see it? Well, the answer is we do see it. It's just that people are not calling it the right thing. They refer to it as cosmological inflation and the acceleration of the universe, or the accelerating expansion of the universe, I think. But what's actually going on is basically Earth is going around in little circles around the sun, and every time we do that, we accelerate one way or the other, causing events far away from us to push outward, and because those events are on our past light cone, they tend towards expansion rather than contraction.